It works now. All right. Um, Thank you so much for having me here. It's very excited. It's actually my first time in person CVPR. As a newcomer, I'm very excited to see how synergize some techniques from computer vision and robotics and control and AI. So the topic today is going to be from Sim2Real 1.0 to 4.0 for humanoid robotic control and local manipulations. This is a bunch of recent work from my group I'm going to present. The first one is called Omnich tool. It's basically a framework that can translate human motions to humanoid motions in real time. And the second work is called ASAP. It's actually a very agile whole body control framework that can replicate very agile human motions like what you saw in this video. And the third work is called FICON. It's a humanoid object interaction local manipulation framework. In this video, the humanoid can open a heavy door, pulling a heavy cart, and interact with human, interact with another humanoid. Okay, let's get started. I will start from talking about something different from Sim2Real. Let's talk about teleoperations or learning from videos because these two methods seems really promising recently. I mean, the recipe is quite simple. What we do is we just do behavioral cloning from labeled actions, meaning that you have either human teleoperation data or some sort of human videos. Then you get labeled action directly from this source. And an action space is typically either joint angle or just in the effector pose. And the low-level control in these settings are, in general, very simple and accurate. You either use very simple linear PD control or use some inverse kinematic, just PD control. So there are two examples. One is like this very famous demo from a startup company called Physical Intelligence. This is like a PAT 0.5 policy from them. They learned this policy from telephone data. You can see it's by the way, all the objects in this video are unseen in the training set. This is very impressive, right? It generalized to open vocabulary and it's pretty amazing. It's learning purely from telephone data. Another example is also very popular demo, I think released 2 weeks ago. It's a new demo from Tesla Optimus. You can see in this video the robot, the humanoid robot Optimus can do a lot of long horizon complex manipulation task. And this is like a little bit different. It's learning from mixed teleoperation data and human video data, meaning that it learn not only from like robot data, also learn from some human data. You can see a pretty impressive demos here. It can do many household tasks. Yeah, like clean the floor, etc. Okay, it's not just like a industry, right? In my group, I also work on similar topics. Like this is a collaboration with Professor Xiaolong Wang's group in USSD. What we're doing is this paper is called Humanoid Policy, Human Policy. So in this video, the diagonal part is humanoid data, humanoid teleoperation data. The non-diagonal part are human data. So what we did is we learned a unified policy using a unified representation space to kind of like to co-train a policy from human data and the humanoid data. Okay, I know you're waiting for however, but yeah. So, but how about tasks involving, I can keep talking about this. It's going to be a VLA talk, but apparently it's not the topic. So how about tasks involving whole body agilities, right? For example, like for this athletic maneuver, like playing basketball or like pulling a cart, push a cart, heavy cart, or like moving, holding and moving a box, right? And we will realize for this task, it's impossible or extremely hard to teleoperate. Actually, if you can, you already solve the problem. Imagine if you can teleoperate a robot pulling a heavy cart or like playing basketball, you already solved the problem. And it's also very hard to get labeled actions, right? Imagine if we ask Michael Jordan, hey bro, I want to learn fadeaway jumper. Could you tell me your jump trajectories? And he will probably think I'm insane, right? It's very hard to get labeled action for free. And also it's very hard to use a simple low-level controller as previous examples like PD or IK for tracking. Meaning that even though you get labeled action like jump trajectory, you don't know how to realize it on your robot. So which basically means all these like human videos or human demos doesn't directly give you robot joint control, right? Robot joint control, the right-hand side is what we actually need to unlock this agility. So to summarize, I think most dexterity and agility, especially talking about the whole body agility, come from system 1 for human, not system 2. Like if you're not familiar with this kind of thing, system 1 refers to some intuitive instinct reasoning and cerebellum, not necessarily brain. And system 2 refers to some slow rational thinking. And I suspect most human demonstrations involve little system 1. I'm talking about like teleoperations, right? Because by definition, when you teleport robot, you're using a rational thinking to control robot. So here comes the questions, how to learn system 1 agility and dexterity. So my answer today is we're gonna need a model or we're gonna need a simulator, and we need to do something called Sim2Real learning. And today's talk, I hope will give you a whole spectrum of Sim2Real learning. So fortunately, like in control community, in robotics community, people have been doing something called a model-based control for many decades. If we think about this, model-based control is literally Sim2Real 1.0. So what we do is simplify model plus online reasoning. So we start from something called a reduced order model, which means like you simplify a very complex robotic system into some analytic equations. For example, for humanoid, you can consider something called inverted pendulum model. For a quadruped, you can consider something called a single rigid body model. They're basically like simplified version of a very high-dimensional dynamical system. And once we have this model, we do something called online MPC, online model pre-control. Basically, you're solving an optimization problem in real time to figure out what is optimal action for the current state. And like if the problem is convex, it's typically easy. You can do something like QP, quadratic programming. If the problem is non-convex, a little bit more tricky. You can do something like sequential concept programming, DDP, ILQR, etc. But the takeaway is like the output of this program is action A, right? It's action. It's not a policy. It's action, and you directly deploy this action on robot, which give you kind of very amazing this MIT cheetah jumping on the table kind of thing. So if you think about this logic, right, I feel this is very fascinating, at least to me. There's no pre-training. So this procedure 100% rely on very fast online reasoning because you need to solve a optimization problem in real time in very high frequency. It's super fascinating, at least to me. But simultaneously, it's also a little bit foolish because it's so different from, like in language model or vision, right? There's no pre-training. So every time you encounter a new scenario, you need to resolve the problem from scratch. So, and right now we can actually do like full order simulators, not just like reduced order models. We can solve full order MPC using advanced sampling-based method. This procedure is very similar. The only difference is we replace the analytic equation in previous slides with a simulator, right? You can use ISAC, NVIDIA ISAC or Genesis or Mojoko, whichever you like, right? Then we do a very massively parallel sampling-based optimizations, right? To sample what trajectory give you good performance, and then I deploy the action in the real world. I give you some interesting performance, like here, the quarterback jumping. There's still no pre-training. This online, solving a problem. This is like a ball, like spinning a ball for Dex hand. This is like humanoid Loco-Manipulation. Again, there's no pre-training. It's no learning essential. It's just online optimizations. So this is like our recently released framework for that called DLMPC, which is best paper award finalist in ICRA this year. So however, right, compared to RL, this procedure is still slow. You need to solve a very big optimal control problem in real time. And even worse, it requires state estimations, right? Because to be able to figure out which trajectory, which action is better, you need to know where the robot is, right? Okay. And here comes reinforcement learning to tackle this challenge. I call it Sim2Real 2.0, right? We start using Sim2Real RL to solve the very same problems. We start from like a physics-based simulator, again, ISAC, Genesis, and Mojoko. Then we create a massively parallel training environment, meaning that we put a virtual humanoid in simulator, and sometimes for robustness, we need to randomize the terrain. We need to add perturbations and perturbation torque, etc. And the key difference is, compared to MPC, what we do here is we train a policy offline to optimize a big optimal control problem. So what we do is we use something called policy optimization, something like, for example, PPO, to optimize the policy pi theta. The input to the policy pi theta is observation O, the output is action, right? We learn this policy using RO. And finally, we transfer this policy, not action, to the real world, right? This whole pipeline is called Sim2Real reinforcement learning. I call it Sim2Real 2.0, right? It's so successful in last 5 years, really because the massively parallel policy gradient method is such a strong policy optimizer that can solve a very complex optimal control problem offline. And another reason a lot of people haven't realized is there's no need for, sorry, some connection issues, seems like. 1 second. I think directly to HDMI might be better. Oh, sorry, my bad. Yeah. Wait, hold on. Okay, sorry about that. Don't know what happens. Yeah, so another thing people haven't realized, which we take for granted for RO, is there's no need for state estimations in this procedure because the observation O is all you need. We don't need to know the state of robot. We only need to know like observations. Yeah. So I'm gonna give you 2 examples for Sim2Real 2.0. One is our, one of our work like last year called H2O, human to humanoid whole body control. And the goal of this paper is we want to build an interface between whole body human motions and humanoid motions. We want to translate what human can do to what a humanoid can do. And we wanted this interface support many different things, right? We wanted to use this interface for whole body teleoperations, meaning that you're real-time teleoperating a humanoid, and imitation learning, and integrating with foundation models like VLAs. And the key idea of H2O is exactly the Sim2Real 2.0 idea I just mentioned from a large-scale retargeted human motion dataset. Okay, I'm gonna play this video first to give you a sense what this framework can do. So this part, my student was wearing Apple Vision Pro to whole body teleoperate the humanoid. At that time, it's still Unitary H1-2. Again, I want to emphasize it's not just upper body teleoperation, it's the whole body teleoperations, meaning that we not only control the upper body, the hand, the arm, also the lower body, the torso, the foot. Yeah, the humanoid walk to the bench. I'm gonna do some interesting manipulation task. Grasp a knife. No worries, it's not going to hurt you. Just cut a cucumber. Yeah. Yeah, this is like a one-shot video because we want to show humanoid is an interesting general purpose platform, right? Can do many different things, from locomotion to local manipulations to manipulations. And this is like stepping back and start sweeping the floor. Yeah. And say hi to you. Can do many different things, like a lot of manipulations, like watering plant, moving basket, and tennis, playing table tennis, badmintons. And this is like boxing, drawing. You can see how teleoperation works here. And this part is not teleoperation. We integrate the framework with GPT-4o to have some autonomous interaction between humanoid and human. And this is also not teleoperations. We train a diffusion policy to make the humanoid autonomous using the whole body control layer. And this is a verbal instruction. We literally talk to the humanoid. Humanoid can react. To publish a humanoid paper, you have to bully the robot to prove your method is robust. So we did that. And also like some outdoor locomotions. This is the same policy, the same neural network can work indoor, outdoor, in many different tasks. Sorry, I'm playing the video too fast, but if you are curious, you can check out the website for more demos. But I want to talk more details how we achieve that. So again, this is Sim2Real 2.0 plus learning from human dataset. I'm gonna give you some more insight. So there are 2 steps. Step number 1 is we need to create a large-scale humanoid motion dataset, not human motion dataset. Your large-scale humanoid dataset didn't exist at that time. So we need to create it. So fortunately, from vision community, right, and graphics community, we already have a very high quality human motion data set, like AMAS, right? Corresponding to the first row in this figure, right? It's a very high quality motion capture data set. And what we did is first we did something called shape fitting. This is like using inverse kinematics from first row to the second row. Basically, we found human models, the simple model that is closest to humanoid. And then we do just pure geometric shape fitting, right? From the first row to the second row. It's why the human in the second row is a little bit weird, but it's closest to humanoid. And after this, it's still not enough because this procedure is only in kinematic level. It doesn't consider physics. So we did another step called physics-based retargeting. So from the second row to the third row. So what we did is we learned a RO policy, a privilege tracking policy, the pink policy here, right? This policy is going to track all the motions in the second row using reinforcement learning. I call this privilege policy because this policy knows all robot states, even in practical. So the idea of this step is we want to generate humanoid feasible motions and filter out impossible motions. For example, the last motion here is definitely impossible for unitary H1. So we just remove it. And the first four are in the data set. So basically this procedure is to kind of like translate what human can do to humanoid can do and have in the ideal case is why we use privilege tracking policy. If you're curious about the ratio, we can actually keep like 90%-ish of the AMAS data set. So we can track like a lot of motions from the AMAS data set. Okay, but this is not enough for Sim2Real, right? Because this policy, this privilege policy is not practical at all. You cannot really deploy this policy in the real world. So we did the second step called Sim2Real RO training. So what we do is also very simple and standard. We distilled the privilege tracking policy, the pink policy, to the blue policy, the deployable student policy. And the student policy only require observations available in the real world. And this is a fairly standard imitation learning procedures. And of course, we add a lot of domain randomizations for robustness. All right, this is basically how it works. I wanna emphasize this H2O pipeline is very flexible and very extendable. I think the major contribution of H2O is we define 3 key steps for learning from human motions for humanoid. So step 1, we need to do some sort of motion retargeting to translate human motions to humanoid motions. And step 2 is we need to sort of like some privileged teacher tracking policy learning to track these humanoid motions. And step 3 is we need to sort of like distill to a student policy that can be deployed in the real world. Each of these steps are very extendable. For example, in step 1, we can change the motion source from mocap to videos, right? We can learn from videos, egocentric videos or like other different videos. And the student policy in step 3 is also very flexible. We can ask student policy to track different key points, or like we can change it to vision-based. Just want to give you 2 examples of follow-up works. One example is a Hoover work from NVIDIA. What they did is they distill one strong teacher policy to many different student policy. So each humanoid in this video is actually corresponding to different like student policy architectures. And another work is a recent work, I really like it, from Berkeley called a video mimic. They changed the human motion resource in step 1 from mocap to videos. They actually can learn from this video in the wild and to translate what human can do in the video to a real unitary driven humanoid. Okay, another examples I want to talk about for Sim2Real 2.0 is the opposite. So all the previous examples are learning from human motions. And this is learning without any motion priors, because we also want to explore how far Sim2Real 2.0 can go without any human motion priors. I don't have time going into detail, but I want to show you give you some insight. This is what we can do. This framework is sort of a COCO. We can learn a lot of like this parkour stuff, like parkour jumpings. Um, and again, just without any motion practice, learning from scratch, reinforced learning from scratch. Like clamping dance is a little bit funny. Uh, and yeah, I guess I'm gonna stop here. So I don't have time going into details, but the high level point I want to make here is if you don't have human motion process, learning could be very hard. You need something else. So the key idea of Vococo is we have to decompose a long horizon skill into a sequence of sub skills, and we learn the sub skills from like the sequence of content goals and task goals. All right. This is like a Sim2Real 2.0, right? Very promising. Translate a reinforcement learning policy from simulation to real world in 0 shot. So what's wrong with it, right? Why we need Sim2Real 3.0 and 4.0? I think there are some fundamental issues. Like Sim2Real gap is large, unintuitive, and really hard to quantify. And this procedure requires very tedious reward tuning, curriculum tuning, and memorization tuning. The best method is still graduate student descent. And it's very hard to encode prior physics, suffer from poor sample complexity, and unsafe. And another point I want to make is this procedure doesn't have any online reasoning, meaning that you learn policy from simulation, you're done, because your policy is frozen in test time. You don't have any test time learning or whatever you call this. Okay, so this is my understanding for what's going on in Sim2Real. So the x-axis is the policy parameters. Let's assume it's 1D for simplicity. The y-axis is performance, and the orange line is the performance in simulation, and the green line is the real performance in the real world, right? And you can see the landscape is very, very complex, and even worse, right? Even though we get a good performance in simulation, see that the blue point, right? The performance in real world could be much worse because of Sim2Real gap, right? Is why I call this blue point bad policy, the star point good policies, right? This is like literally what happens in Sim2Real. So to summarize, there are two challenges, right? Challenge number one is very large Sim2Real gap, meaning that the gap between the orange curve and the green curve is huge. And challenge two is this landscape is very nasty, and reinforcement learning could easily hack it, right? Could easily give you some solution that looks okay or very good in simulation, but horrible in real world. So how do we solve this? One answer is you can have human in the loop, right? You can have graduate student in the loop and to keep tuning. But I'm going to offer different solutions. I call it Sim2Real 3.0, right? One idea is we can do real to sim, right? To reduce the Sim2Real gap. Another idea is structured reinforcement learning, right? We can add priors and inductive bias to have a smoother landscape. Okay, let me start from like Sim2Real 3.0, real to sim. So the idea, right, we need to create a feedback loop between the simulation and real world. We want to learn something from real world to bridge the gap in sim and real, right? We need go from real world back to the simulation. So fortunately, people have done that in other robotic platforms in control and robotics community, right? For example, I've done a lot of this kind of thing in my PhD. Basically, what we did is you can learn a residual dynamics term. You can learn a residual dynamic term to approximate this residual dynamics F, right? And then you can design a controller, and this works pretty well for quadrotor, for quadruped. For example, like this neural lander work, NeuroFly, and this area manipulation stuff. So how about humanoid? Can we do the same thing, right? Can we learn a residual dynamics F hat from real world, and we augment simulation to be F sim plus F hat, right? We actually tried, but seems like directly learning dynamics is not a good idea for humanoid, because the learn dynamics F hat has to generalize well, which requires a lot of real world data, which is infeasible. And we also need to regularize F hat heavily, because you need to ensure the F sim plus F hat, this hybrid dynamics still makes sense, which is in general very hard. And don't forget, we have a naughty boy called reinforcement learning, like something like PPO, right? The F hat will be exploited by RO. So we need to be very careful So this is still very hard. I'm not trying to say it's impossible, but we figured it's very hard given existing data and hardware. So what we do is we offer alternative solutions, learning a delta action model, not learning a delta dynamics model. So we call this framework ASAP, learning a delta action model to match Sim2Real. So what we do is the following. We pre-train a policy pi in simulation, and we rule out this policy in real world. We get a state and action trajectory. The superscript R referred to real world. And then we replay the action trajectory AR in the simulation, and we get another trajectory XS, right? The superscript S refers to simulations, right? Because we have Sim2Real gap, the XS will be different from XR. Otherwise, your simulation is perfect. Then what we did is we learned a delta action model, delta A, in simulation, right? Such that if we augment the real world action trajectory with delta A, the resulting trajectory in simulation, XS, is very close to the trajectory in the real world. Meaning that delta A is kind of like bridge the raw trajectory in simulation and the actual trajectory in the real world. Yeah, and delta A is a neural network. So once we learn delta A, you can imagine that deploying pi plus delta A is very close to pi in the real world. So what we did is we we freeze delta A when we fine tune pi in simulator, and finally we deploy pi only in the real world. Yeah. So I want to show you some result. This is like a humanoid single leg balancing problem. And you can see the left video is before learning delta A. I want you to pay attention to the ankle part. If the left foot, you can see it works, but the ankle shake a little bit here, like the left foot ankle. And the right video is after we learn delta A. You can see it can do the same thing, much more stable. Yeah, I want to play it again. The left is before we fine tune the policy in delta A. The right is after. Okay. And we can, this framework works for very agile whole body human motions like this Kobe Bryant fadeaway jumper. We actually slowed down the video. It's not real time. We slow it down to make it, just look better. And this is like a, jumping and 180 turn. Yeah. Okay. I'm going to quickly talk about the second idea in Sim2Real 3.0, which is called structured RL. The idea is we can add some structures in the policy architecture to make it generalize better. The goal is we wanna make the orange line and the green line here more smooth. So the framework I'm going to introduce is called FACON. The task here is heavy duty local manipulations. And this is like the baseline can do for what baseline can do for pulling a heavy cart. You can see the robot barely moves because the cart is too heavy, it's 100 kilo. And this is what our framework can do. It's a very small humanoid robot called Booster T1. It can drag a 100 kilo, almost 100 kilo cart. This is like a door opening. You can see this is the baseline. Again, the door barely moves because the door is 60 kilo. It's pretty heavy. And this is our method. You can see the humanoid walks there and pull the door using left arm and create enough clearance and push the door using right arm and walk in. All right. So the key idea is the key idea is we have a dual agent reinforcement learning framework. What we learn is two policies, two value functions, two critics, and two set of rewards. One policy for upper body, one for lower bodies. Yeah, and we figured this architecture corresponded to humanoid dynamics, give you much better generalizations. I will skip this part. I want to mention that a very similar architecture also works for very challenging and effective stabilization problems. We found it's not just like upper lower body decomposition, also like different frequency helps. So in this project, we ask a humanoid to hold my beer, and humanoid can actually do that without spilling the liquid. And upper body, we use a much higher frequency inference And the lower body, we use a slower policy inference. I just want to play this video. You can see we push the humanoid, and the left arm is using baseline. You can see it's not very stable. The right arm is using our method. You can see the drink is still in the bottle. It didn't spill the drink. And you can see like the humanoid is hold a lot of chips and didn't drop because we can stabilize in real time. I mean, upper lower body can compensate each other and have some interesting emerging behaviors. Yeah, just want to play again. I think it's pretty cool. Again, it's slow motions. Yeah. I think this probably is beyond human to some extent. Yeah. All right. Just want to zoom out a little bit for last minute. So I want to summarize all the methods I present today in Sim2Real into two axes. The x-axis is the simulator or model fidelity or diversity, right? We start from like reduced order model in control and robotics community to full simulator to sim plus real to sim augmentation to generative simulations, world model, etc. And the y-axis is when learning happens, right? Learning could either happen purely offline or purely online, right? Online reasoning or like hybrid. Right, in Sim2Real 1.0, we use nonlinear MPC for a reduced order model for pure online reasoning. Sim2Real 2.0, we use reinforcement learning for offline training. And in Sim2Real 3.0, we use structured RL with augmented simulations. So what I propose is we should go towards Sim2Real 4.0, meaning that we have better models, better reinforcement learning algorithm, definitely beyond PPO, and better online reasoning. So I really think combining offline online could be very powerful, right? What finally I wanna conclude by showing some combining reinforcement learning and optimal control could be very powerful, even if the optimal control part is reduced order. This is like some quarterback parkouring stuff we did 2 years ago, which combining reinforcement learning and some online optimal control. And we found this is much more stable and much more robust. Okay, thank you very much. And everything I present is open source, so check out our lab's website for reference. Thank you so much. Yeah.
We'll probably have time for one quick question. So anyone? I will do the question. I see you have done a lot of like amazing jobs on like learning controls and reinforcement learning. So I was kind of curious, how do you see the current VLA trends, like especially using the robust perception for like dexterous interactions and all those sorts of stuff? Do we have to do multipacks to capture all the interactions, or maybe we just rely on RGB as well?
I think that's a good question. Just by the way, I don't think they conflict. So I don't think like the Sim2Real whole body control stuff conflict with VLA. I feel VLA is more learning the system two, robot learning kind of thing. It learns like it's very good for understanding the thing, right? 3D things and long horizon, this kind of thing is more system two. And reinforcement learning control is more like for system one. I think at some point we're gonna synergize them together. I think a lot of companies are already doing that. For example, like Figure, 1X, Tesla, I think they're already doing that. So, but what is unclear to me is what is interface between them. I think that's a very important research question we need to study. Are we gonna do tracking or are we gonna do some other representation? That would be very interesting. Yeah. Okay, I guess for the sake of time,
Okay,
yeah.
cool. Let's thank Professor Wang. Okay.